Welcome to today's paper reading. Today's paper is titled, Made to Order, Discovering Monotonic Temporal Changes via Self-Supervised Video Ordering. This paper was published on AR14 by Charig and colleagues from the University of Oxford and Shanghai Jiao Tong University. The primary goal of this research is to identify and pinpoint temporal changes in a series of images that are monotonic, meaning they consistently change in one direction over time. To accomplish this, a straightforward proxy task is employed, ordering a shuffled sequence of images. Time serves as a supervisory signal in this task, as only changes that are consistent with the passage of time can lead to the correct sequence. A transformer-based model is introduced to handle sequences of arbitrary length, equipped with built-in attribution maps. This model is trained to successfully detect and localize monotonic changes while disregarding cyclic and stochastic variations. The applications of this model span multiple domains, including the detection of both object-level and environmental changes in previously unseen sequences. Additionally, the attention-based attribution maps generated by the model serve as effective prompts for segmenting the regions undergoing change. Figure 1 illustrates the localization of monotonic temporal changes in satellite images. The top part of the figure shows satellite images taken months apart, highlighting various changes, including monotonic ones like urbanization and cyclic ones like water level variations. The bottom part displays the model's attribution map, which successfully identifies regions with monotonic temporal changes in green, while ignoring seasonal and sporadic changes. This model is trained without manual supervision and demonstrates its ability to generalize to unseen sequences, with the attribution map serving as a prompt for segmentation tasks. The paper introduces a new task of identifying and localizing changes in image sequences that are correlated monotonically with time, while being invariant to other changes. This is achieved through a self-supervised proxy task where the model learns to order shuffled video frames, thereby identifying relevant monotonic cues and ignoring irrelevant changes. The proposed solution is a transformer-based model with a DTR-like architecture that generates an attribution map, allowing the model to generalize to unseen videos in the same setting. In the field of computer vision, self-supervised learning has gained significant attention, particularly in representation learning. The primary goal here is to enhance downstream performance through supervised fine-tuning or linear probing. However, there is a growing interest in going beyond representation learning to directly learn useful tasks under the self-supervised setting, such as depth estimation, optical flow, correspondence, and sound localization. This paper builds upon this paradigm, enabling the deployment of models to downstream tasks without the need for labels. Additionally, temporal ordering is explored as a supervisory signal, with alternative cues like speed and uniformity also being leveraged. The focus is on advocating temporal ordering as a task in itself, demonstrating that localization can emerge using time as a supervisory signal. Figure 2 illustrates the network architecture designed for ordering an unordered sequence of F-frames, each divided into N patches. The transformer encoder processes all Fn patches as input and outputs Fn features. The transformer decoder employs Q-learnable queries, each representing an ordinal position, and cross-attention with the encoder's output to produce Q features. A cosine similarity matrix is computed between the encoder and decoder features, and spatial max-pooling over this matrix yields F times Q order predictions. The final ordering is determined by taking the argmax along each query axis. The example sequence shows the hour hand, which is monotonically correlated with time, localized in the attribution map. The primary objective of this method is to train a vision model capable of localizing changes in an image sequence that correlate with time and ordering the sequence. The model is designed to output an attribution map and an ordering of the images. The architecture proposed to achieve this is based on transformers, consisting of an encoder and a decoder. The encoder processes image patches, while the decoder aligns these patches to predict the correct temporal order. The model computes a cosine similarity matrix to generate the attribution map. During training, a temporal loss is used, which includes reversibility to aid in learning. At inference, the model predicts the order by taking the argmax along the query axis. The architecture is also designed to generalize to sequences of different lengths, though it has a maximum limit. Figure 3 provides an overview of the sequence datasets used in the study. From left to right, the datasets include dynamic random dot stereograms, RDS, featuring moving dots, moving camouflaged animals, MoCA, time-lapse clocks in both cropped and full versions, time-lapse scenes, MUDs, CAL FIRE, and OASIS 3. Each dataset represents a different type of temporal sequence, from synthetic moving dots to real-world scenes like camouflaged animals and outdoor time-lapse videos. This diversity in datasets allows for a comprehensive evaluation of the model's ability to detect and order temporal changes across various domains. In this section, we discuss the various datasets used in our experiments. For video datasets, we utilize dynamic RDS, MoCA, and time-lapse analog clocks. These datasets were chosen to explore different temporal cues and their impact on model training. For temporal image sequences, we focused on MUDs, CAL FIRE, and OASIS 3, which allowed us to study long-term changes in geographical and medical data. Lastly, for image ordering datasets, we evaluated our method on multi-digit NIST, SVHN, and standard benchmarks, which tested the model's ability to order images based on absolute criteria. Figure 4 illustrates the evaluation of localization and segmentation performance by manually annotating the monotonically changing regions on the MUDs test set. Each sequence consists of 4 frames, with the changes between the first and last frames highlighted in yellow. Additionally, the figure showcases the 4-digit NIST and SVHN datasets, where the task involves ordering the images based on the numbers they contain in ascending order from top to bottom. Table 1 provides a comprehensive overview of various datasets used in the study, detailing their attributes and the performance of the model on unseen sequences. The datasets include dynamic RDS, MoCA, clocks, both cropped and full, time-lapse scenes, MUDs, CAL FIRE, and OASIS 3. The performance is measured using exact match, EM, and element-wise, EW, metrics, which evaluate the accuracy of the model's ordering predictions. Each dataset is characterized by its sequence length and the type of cue it provides, such as motion, clock time, or scene changes. This table is crucial for understanding the breadth of the study and the model's ability to generalize across different types of temporal data. The model's performance in ordering video frames is evaluated through EM and EW scores, which are detailed in Table 1. Qualitative results are also provided in Figure 5, demonstrating the model's capability to order sequences effectively across various datasets, especially in scenarios with significant changes. For temporal image sequences, the model identifies ordering cues such as road construction and forest fires, showcasing its utility in remote sensing applications. Additionally, in MRI scans, the model detects age-related changes in the brain, aligning with existing literature. However, there are limitations, such as the model not enforcing a one-to-one matching between queries and images, leading to some images being associated with multiple queries or none at all, as illustrated in Figure 6b. This issue can be mitigated by ensuring each image is predicted once, but recognizing that not all sequences can be ordered provides valuable information, treating invalid orderings as a means to assess sequence orderability. Figure 5 presents the results of ordering and localization across various datasets. The model successfully discovers and localizes various cues in different domains, such as object motion, clocks, scenery, landscape, and biological aging. The left column displays the input images in an unordered sequence. Each column of the similarity matrix corresponds to the model's prediction for each individual order, numbered from 0 to 3. The image highlighted in the red box is the chosen one, and the attention heat map within this box precisely localizes the change. This demonstrates the model's capability to accurately identify and highlight temporal changes while remaining invariant to unrelated cues. Figure 6 illustrates 2 key aspects of the model's performance. Part A shows how the attribution map is utilized to prompt the segment anything model, SAM, to generate segmentation masks, which is crucial for identifying and localizing specific features. Part B presents examples of unorderable sequences, distinguishing between sequences that are too static and those that are too stochastic. These cases highlight a limitation of the model, where images may be claimed by multiple queries or none at all, indicating the need for a one-to-one matching strategy. This inability to order certain sequences, however, provides valuable information about the nature of the data, such as sequences that cannot be ordered due to their static or highly stochastic nature. Figure 7 presents a comparison of segmentation methods, specifically focusing on Siamese networks, 27, and change vector analysis, CVA, 43. The figure illustrates that supervised methods, like Siamese networks, tend to ignore changes that are not related to buildings, leading to undersegmentation of urban development changes. On the other hand, pixel-based methods such as CVA over-segment regions that exhibit non-monotonic changes, including seasonal variations and water level changes. In contrast, our model effectively highlights monotonic changes in the environment, such as urban development, while remaining invariant to other types of changes. This capability demonstrates the model's superior performance in accurately detecting and segmenting relevant temporal changes. Table 2 presents the localization and segmentation results of various methods, focusing on the pointing game accuracy for localization and the mean intersection over union, MIU, for segmentation. The table highlights the performance of methods such as monomods, RDS, MoCA, Siamese networks, CVA, DCVA, and our proposed methods with and without enhancements like DINO-V2 and SAM. Key metrics include localization accuracy, ACC, and segmentation MIU, showing that our methods, especially when combined with DINO-V2 and SAM, outperform others in both localization and segmentation tasks. This table is crucial for understanding the effectiveness of different approaches in accurately pinpointing and segmenting changes in urban development tracking and change detection tasks. Table 3 provides a detailed comparison of various self-supervised methods in terms of their performance on localization and segmentation tasks using the monomods dataset, as well as their effectiveness in fine-tuning for building change detection on the MUDS dataset. The table highlights the accuracy of localization, LOC, the mean intersection over union for segmentation, SEG, and the F1 score after fine-tuning, for each method. This comparison is crucial for understanding the strengths and weaknesses of different self-supervised approaches in handling temporal and spatial data, particularly in the context of urban development and change detection. Table 4 presents the performance of various methods on the task of ordering images of numbers in increasing order across two standard benchmarks, NIST and SVHN. The metrics used for evaluation are EM, exact match, EW, exact weight, and EM5, exact match at length 5. EM and EW are evaluated at the sequence length the model has been trained on, which can be 5, 9, or 16. EM5 specifically tests the model's ability to generalize to a test sequence length of 5. The results indicate that our method outperforms others in terms of ordering accuracy and generalization capability. In this paper, the authors explore using time as a proxy loss for self-supervised training of models to discover and localize monotonic temporal changes in image sequences. Future research could extend this work by discovering more complex temporal changes, such as seasonal or periodic variations, as well as object state and attribute changes. Additionally, investigating how the model scales with larger datasets and computational resources, and exploring new applications enabled by this task, would be valuable. Overall, the authors hope this paper serves as a valuable starting point for future research and applications in this area. The authors would like to express their gratitude to Tingda Han, Raghav Sachdeva, and Alexander Shtedritsky for their valuable suggestions and proofreading efforts. This research has been supported by the UK Engineering and Physical Sciences Research Council, EPSRC, Centre for Doctoral Training, CDT, in Artificial Intelligence and Machine Learning, AIMS, under grant number EP/S024050/1, as well as the UK EPSRC Programme Grant for Visual AI under grant number EP/T028572/1. Thank you for watching.